Hi students, this is going to be Introduction to an Application of Integration. That's specifically starting with a derivative equation and trying to go from there to figure out what that original equation was. These are called differential equations, and they are a way for us to solve for total quantities if we only know things about rates, which happens a lot in the world around us. So the first thing we're going to do is to, that's weird, didn't mean for it to change that much, is to try to get the same variables on the same sides of these things. So anything with y, we're going to try to put on the y side. Anything with an x, we're going to try to put on the x side. So I'm going to multiply both sides by dx. And then I've got dy is equal to k times y times dx, and I'm going to divide both sides by y. I'm going to rewrite the left side as 1 over y and then dy, and on the right side we've got k times dx. This is called separating variables. We've grouped the y stuff with y. I leave the constant with the x just to make that a little bit easier to deal with. So our next step is to try to get rid of these expressions and convert them into something more useful. And to do that, we're going to integrate both sides. The thing that's a derivative of 1 over y would be ln, and again, we need absolute value just to make sure that our domain is okay. And I need a plus c there. And on the other side, this is just a constant. So this is like what's the function that's a derivative of 2? Would be kx, and then plus a constant. And here we end up in kind of a bit of a pickle because we have two constants in here. One of the things that we often do is treat it as though we're then combining these two constants. Because if these are just numbers, and by just numbers I mean just constants, if I were to combine them, it's just going to make another constant. So I could call this constant 1, constant 2, and then if I were to move this, oh man, it's not going to let me erase that unless I do a special erase. There we go. So if I were to move this constant over to this side, we could call that constant 3 if we really wanted to, but to be honest, we can't tell the difference between constant 1, 2, or 3. And we end up looking at this as an equation. Okay, I still want to get y by itself, so let's do that. I know to undo a natural log, I've got to convert this to an e form, because natural log is the same thing as saying log base e of the absolute value of y is kx plus c. So I'm going to rewrite this as e to the kx plus c is equal to the absolute value of y. And what we end up getting out of this, since we have absolute value, that's really looking at a plus or minus version of this e to the kx plus c. At this point, our equation has been solved. We'll be able to figure out if this is positive or negative at a later point. We call this actually, I don't know why I put the arrow there, the general solution, because we're looking at this as any possible number we could use for that c will make this work. All right, here's a couple more for us to play with. And I may come up with another couple examples just to do for some extra practice. Okay, so I've got to start by separate variables. And I'm going to have sine of y dy is equal to negative 1 dx. Then we're going to integrate. I'm going to take the antiderivative of both sides. Antiderivative of sine is going to be negative cosine of y. On this side, negative 1, well, that's going to turn into negative 1x. And I need to remember my plus c always. Again, I'm only going to include this on one side. I could write this as plus c, and then combine them. I'm not going to bother with that. I might just get rid of my negative part here, though. So what my goal is now is to solve for y. So let's make this positive, and make that negative. It doesn't matter if you have plus c or minus c, but I'm just going to make that minus c for the sake of making that a little bit easy. And to undo cosine of y, we're going to find the inverse cosine, or the arc cosine. At this point, this problem is done. And again, this is a general solution. We talked about particular solutions with slope fields. In order to get a particular solution, we would need a specific value to figure out what's going on there. For number 2 on this page, and I actually think that I'm going to do this on the next slide. So 2x over e to the 2y. X over e to the 2y is equal to dy dx. Okay. Same thing, I'm going to combine like terms by separating. We end up getting e to the 2y is equal to 2x dx. And I lost my dy, sorry. Then we integrate. The thing that has a derivative equal to e to the 2y is going to be e to the 2y divided by 2. The thing that has a derivative of 2x is going to be x squared, and I need my plus c. Okay, let's solve for y here. So I end up with 2, let me write my e stuff first. E to the 2y is equal to 2x squared plus 2c, which I could write as c or 2c, doesn't actually matter. And then to convert this, I need to put this into log form. So I end up with 2y is equal to ln of 2x squared plus 2c. And I'm going to go one step further to get y by itself. And we get ln of 2x squared plus 2c over 2. At this point, the problem is done. Okay, let's do one more example. Just as a note, there are a lot of problems to work on in the link on the previous page. So those are definitely worth doing some practice for. So for the last one, it's going to be really similar to the first one that we saw, and I want to take this one step further. I'm going to get this as dy over y is equal to 2 dx. I like getting the y as much by itself as possible at first. That makes our lives a little bit easier for dealing with this later. Okay, and then when we do this, we end up getting 1 over y dy is equal to 2 dx. When we integrate, 1 over y is going to be ln the absolute value of y, and 2 is going to be 2x. I'm going to do my plus c on my right side. To get the y by itself, we're going to exponentiate both sides. So we get absolute value of y is equal to e to the 2x plus c. What I really wanted to do here was to talk about this e to the 2x plus c thing, because there's a cool thing that we often do in calculus. And writing this as e to the 2x times e to some constant. We can use an exponent rule to break that up. And then e to some constant is just another constant. So we often write this as c e to the 2x. And then if we got the absolute value, go on, that's plus or minus ce to the 2x, depending on the initial value that we have. We do this to make this an easier problem to look at. If you spent some time in other classes, you might look at this and see like the PERT formula, dealing with continuous interest, and that's where that comes from. All right, I decided to add in a couple examples of particular solutions. That's where we have not just the general solution that we're going for, but we're trying to get a specific value. So here we're told that y of 1 is equal to ln of 3e minus 1. So we have the point 1 comma ln of 3e minus 1. All right, that's going to let us figure out what c is once we have a general solution. So let's go back to our thing here. We have x minus y in the exponent. That looks kind of gross. I'm going to rewrite this as 3e and x minus y. That means that we divided stuff. So 3e to the x over e to the y. And then when we separate our variables, we're going to move the y stuff on the other side. We got e to the y dy is equal to 3e to the x dx. We do our integration. E to the y is going to be e to the y. 3e to the x is going to be 3e to the x and then plus some constant. And I'm going to get y by itself here. I could either plug this in now to figure out what c is, or I could get something by itself so we can just jump to the end of this. And I think that's the way I'm going to go here. And to go from e to the y, I'm going to convert this to ln. So we've got y is equal to ln of 3e to the x plus c. Here's my general solution. That's where we stopped in the other problems. For the particular solution, I'm going to use the points that we were given. And I'm going to rewrite this to solve for c first. So ln of 3e minus 1 is equal to ln of 3e to the 1 plus c. And you might see based on this that c would have to be -1 to make this work. So my particular solution is going to be y is equal to ln 3e to the x, and then c was -1. One more to look at some particular solutions, and I'm going to do the same stuff here. Separate first. We're going to have 1 over y squared dy is equal to 2x dx. Then when we go to integrate, okay, this is really y to the -2. So that's going to be y to the -1 divided by -1. On the other side, 2x is going to be x squared and then plus c. I'm going to move the negative to the other side to get 1. I'll also make this 1 over y is equal to -x squared minus c. I could multiply both sides by y, divide by -x squared minus c, and get y is equal to 1 over -x squared minus c. This is my general solution. To get the particular solution, I'm going to plug this stuff in. This is the point 3 comma -1/12. So -1/12 is equal to 1 over -3 squared minus c. -1/12 is equal to -9 minus c on the bottom. C has to be 3 in order to make this work. So my particular solution for this would be y is equal to 1 over -x squared minus 3. This is my particular solution.